So last session, we focused on assigning oxidation numbers and just doing basic analysis of redox equations. So our goal here is to assign oxidation numbers for each atom in the following redox reaction. We're to identify the oxidizing and reducing agent, and then our goal is to write oxidation and reduction half reactions. So first things first, we have to go through and we have to assign oxidation numbers. So starting with hydrogen, what is the preferred oxidation number for hydrogen? What is the preferred oxidation number for hydrogen? +1, yep. What is the preferred oxidation number of oxygen in most cases? -2, exactly right. So let's just go through and put a -2 for the oxidation number of all of our oxygens. We don't have any of the exceptions for right now. Okay, now let's do the easy ones. What's the oxidation number of chlorine in chloride? What's the oxidation number of chlorine in chloride? Or more specifically, what's the charge of chloride? -1, yep, exactly right. Okay, so let's keep going now. Let's look at thiosulfate. Let's look at thiosulfate in detail. So we know that our total charge, so what is our total charge for thiosulfate? What is our total charge for thiosulfate? Yep, -2, exactly right. Okay, and our total charge is equal to the number of sulfur atoms, which is 2 sulfur atoms, times the oxidation number of sulfur, plus the oxidation number of oxygen, which is -2, times the number of oxygen atoms. So if we solve for the oxidation number of sulfur, we get our total charge, which is -2, minus the oxidation number of oxygen times the number of oxygens divided by the number of sulfurs. And that in turn gives us an oxidation number of +4/2, which gives us +2. So sulfur has an oxidation number of +2. Okay, let's keep going now. In hypochlorite, let's try to figure out the oxidation number of chlorine in hypochlorite. So we're going to use the same formula. So the oxidation number of chlorine is equal to the total charge. And what is the total charge in this case? What is the total charge in this case? -1, exactly right. I have -1, okay, minus the oxidation number of oxygen, which is -2, times the number of oxygen divided by the number of chlorines. And that in turn gives us an oxidation number of +1. Allow me one moment just to quickly reset OneNote, just because I'm noticing there's a small amount of delay. Okay, perfect. Everyone can still see the OneNote being shared after I reset it, right? Okay, perfect. So we have assigned the oxidation number of chlorine as +1. Let's look at the oxidation number of sulfur in this dimeric species. So again, our total charge is -2. We have, so oxygen's oxidation number is -2. We have 6 oxygens and we have 4 sulfurs. Now, this calculation really shows us an important point to consider. Oxidation numbers can be fractions. So in this case, for example, we have an oxidation number of 10/4 or 5/2 for sulfur. Okay, so now that we have all of our oxidation numbers established, I'm going to rewrite our equation. I'm just going to rewrite our equation. And then we're going to pay attention and we're going to look and see. We're going to look and see where do we have a change in oxidation number. So we have the following oxidation numbers. And looking at this equation, in detail, my first question to all of you is there an atom that increases in oxidation number? Is there an atom that increases in oxidation number? And if so, what atom increases in oxidation number? What atom has its oxidation number increase? Sulfur, exactly right. Okay, so let's isolate sulfur. So we have S2O3, 2-, leading to S4O6, 2-. So we went from +2 to +5/4, +5/2, which can be best thought of as +2.5. Now, this is the change per 1 sulfur atom. So we have a change of 0.5 electrons per sulfur atom. And how many sulfur atoms are participating in this redox half reaction? How many sulfur atoms do we have? How many sulfur atoms do we have? Just counting, how many total sulfur atoms do we see? 4, okay? So we take 0.5, which is our net change in oxidation number, times 4, which gives us 2 electrons. Now, if our oxidation number went from +2 to +2.5, do we put our electrons on the reactant or product side? Did we gain or did we lose electrons? Did we gain or did we lose electrons? So if our oxidation number increases, so let's discuss this. So our oxidation number increased, ergo we lost electrons. So we're looking at an oxidation half reaction. So we place our electrons on the right-hand side. If our oxidation number increases, you place your electrons on the right-hand side. Does that make sense to everyone so far? Does that make sense? So if your oxidation number goes up, you lose electrons, your electrons go on the right. Let's look at our other half reaction. Is there any species where our oxidation number decreased? So if our oxidation number decreases and we gain electrons, what species is gaining electrons? What species is participating in a reduction half-reaction? What atom is gaining electrons? What atom is having its oxidation number become more negative? Just compare the oxidation numbers on the left and right hand side. So let's go through. Oxygen, 2 and 2. I see a lot of people typing chlorine, exactly right. So we're going to put both species that have chlorine into our half reaction. And our chlorine went from +1 to -1. So how many electrons did we gain? What's our net gain of electrons in this case? How many electrons did we gain? 2, exactly right. And as we can see very clearly, do we have 2 electrons in both of our half reactions? Do we have 2 electrons in both of our half reactions? Are electrons conserved? Do we have the same number of electrons on each side of both of our half reactions? Yes, so we're good to go. Let's do another example. So this time I'd like you to work through the following example using our previous guided problem solving sessions as a reference. I'd like to assign oxidation numbers to each atom, identify the oxidizing and reducing agent, and write the oxidation and reduction half reactions. So just as a reminder, so the oxidizing agent will gain electrons, and the reducing agent will lose electrons. So let's take a moment, let's look at the following equation, and I'd like you to message me in chat either the half reactions, or you can identify the oxidizing and reducing agents, or you can message me the change in oxidation number for each of our species in this reaction. So take a few moments and assign oxidation numbers to each atom in the following equation, and we'll discuss in about 3 to 4 minutes. And don't be shy to message me with questions, but I'd like to see a few proposed solutions and at least a few identifications of the oxidizing and reducing agents. And you're even welcome to message me your proposed half reaction. Any questions so far? And don't be shy to message your proposed identification for the oxidizing and reducing agent. And we'll discuss this in about another minute. Just want to give everyone time to formulate their own response. So that way when we discuss, you can compare your work to our solution. And so that way we can address any potential parts of this problem-solving exercise that we need to clarify. Though I really would like to see a few proposed solutions. Don't be shy, it really helps me get a sense into your logical process, and it helps me comment on some things to pay attention to when balancing and solving these redox reaction problems. So to help provide a little bit more guidance on this problem, let's look and let's together assign oxidation numbers. So looking at aluminum, what is the oxidation number of the pure element aluminum? The oxidation number of the pure element aluminum. 0, yep, okay. What's the oxidation number of hydrogen typically? Yep. +1. What is the oxidation number of oxygen typically? -2. Okay. What about aluminum in aluminum hydroxide? So if we break apart aluminum hydroxide, what is the theoretical charge of aluminum in this case? What is the theoretical charge of aluminum? +3, yep. Oxygen is still -2, hydrogen is still +1. Perfect. Okay, what is the oxidation number of hydrogen in pure hydrogen gas, in the elemental form of hydrogen? What is the oxidation number? 0, yep. Okay, perfect. So, let's now look and let's see what atoms increase in oxidation number. So what atoms increase in oxidation number? Okay, so if we increase in oxidation number, we're looking at an oxidation half-reaction, and this is describing our reducing agent. If you had to take a guess and you really were unsure where to start for what the reducing agent is, it will overwhelmingly be a metal. Overwhelmingly, in the majority of the cases you see. So we have aluminum solid going to aluminum 3+. Now, how many electrons have we lost per aluminum atom? How many electrons have we lost in a single aluminum atom? 3. So we have 3 electrons per aluminum atom. And how many aluminum atoms are participating in this reaction? How many aluminum atoms are participating? 2. So then that gives us 6 electrons total. Now, if we're losing electrons, what side of the equation are we going to put our electrons on? The left or the right? If we're losing. And another way to think about it, we are giving electrons. So what side should they go? On the left, on the reactant side, or the right, the product side? Are we another way to think about it, are we gaining or producing electrons? Are we gaining or losing, producing electrons? So what side should it go? Okay, so if we're it should go on the right, exactly. If we lose electrons, electrons are on the product side. Okay, let's look at other species in this molecule. What atoms are gaining electrons? What atom is going down in oxidation number? What atom is going down in oxidation number? What atom is getting a more negative or a smaller oxidation number? Hydrogen, yep. Okay, so let's put all the species involving hydrogen. So we have H2O, liquid, leads to 3H2 gas plus 6OH minus aqueous. Don't worry about the hydroxide for now. This is just bookkeeping to balance our atoms. Let's focus on hydrogen. So we went from +1 to 0. So what is our change per, how many electrons have we gained per hydrogen atom? So how many electrons have we gained per hydrogen atom? 1, yep. Okay. And how many hydrogen atoms have participated in this redox process? How many hydrogen atoms have participated in this redox process? 6, yep. Because 3 times 2 is 6. So we have 6 electrons. And do we place those 6 electrons on the left-hand side or the right-hand side? Are we gaining or losing electrons? We place them on the left because we're gaining electrons. So let's write our descriptor. So we have a decrease in oxidation number. So this is a reduction half reaction. And we're looking at our oxidizing agent. Does that make sense to everyone? Is everyone comfortable with this idea? Can we see very clearly, are electrons conserved? Do we have the same number of electrons on each side of our equation? Yes, we have 6 electrons each, so this is a perfectly balanced redox reaction. We'll talk more about the minutiae associated with where to place hydroxide and water in redox equations, but for now I see everyone slowly developing the skill of counting electrons and checking that these redox reactions are balanced. Okay. So we're going to skip this next example and we're going to talk a little bit about how to balance redox reactions. So suppose you're starting and you're looking at these equations from scratch. How do you balance a redox reaction? Well, first things first, you write the skeletal net ionic equation. You're then going to assign oxidation states to all atoms. You're going to note, and you're going to carefully note any atoms that increase in oxidation state, that lose electrons and are oxidized. You write all atoms that increase in oxidation state in our oxidation half-reaction. Then what we're going to do, and I'm going to use a different pen color for this, we're going to note any atoms that decrease in oxidation state, gain electrons, are reduced. You write any atoms that decrease in oxidation state into the reduction half-reaction. Finally, we do some bookkeeping and we write the number of electrons gained or lost by each species. So if we lose electrons, the electrons are on the product side. If we gain electrons, the electrons are on the reactant side. So electrons are on the product side if we're looking at an oxidation reaction. Electrons are on the reactant side if we're looking at a reduction half-reaction. Does this make sense so far? Now I know it seems like that's a lot of steps. How do they work in practice? Well, we're not quite done yet. So once you have all of your electrons accounted for, we're next going to focus on balancing atoms. So you're going to balance all atoms except for hydrogen and oxygen atoms. Then we have to balance hydrogen and oxygen. And here is where you're going to have to look for some keywords. So if you see the word acidic conditions, you balance oxygen atoms by adding water to each side, and then, and only then, you balance hydrogen atoms by adding H plus to either side of the chemical equation. This is a unique quirk of half reactions and a unique quirk of redox reactions. You can add water and H plus to either side of the chemical equation to balance a redox reaction, and only a redox reaction. So if you see acidic, think water and H plus. If you see the word basic, I'd like you to think OH. Now there's a trick. To this. You balance your oxygen atoms by adding hydroxide ions, and then you balance hydrogen atoms by adding water to either side. Now, in practice, this is probably one of the better tips I can give you that will save you a lot of grief. You may want to become familiar. This is a quote-unquote cheat sheet for basic conditions. So if you want to add one oxygen atom to the left-hand side, you add the following to your chemical equation. You add 2 hydroxides to the left and 1 water to the right. If you want to add 1 oxygen atom to the right, you add 1 water to the left and 2 hydroxide to the right. If you want to add 1 hydrogen atom to the left, you put water on the left, hydroxide on the right. So this is your cheat sheet, but a far easier method for basic conditions is that we play a bit of a pretend game. We balance the basic equation as though it were under acidic conditions. Okay? Then we add hydroxide to each side of the chemical equation to convert all H plus to water. In other words, you add hydroxide to each side equal to the number of H plus ions. So let me give you an example here. So let's suppose we have the following reaction and that we need it to be balanced under basic conditions. Okay, so my question to all of you is, how many OHs, how many hydroxides do I need to add to each side? If I want to get rid of this H plus, how many hydroxides do I need to add? How many hydroxides do I need to add? So we add hydroxide to each side equal to the number of H plus ions. So then, how many hydroxides do I need to add? How many H pluses do I have? 2. So I add 2 hydroxides to each side. This H plus and hydroxide combine together to make 2 waters. So we have the following equation now. We have 2 H2O liquid plus ClO minus leads to Cl minus. Let me rewrite this really quickly. So we have 2 H2O plus hypochlorite leads to chloride plus water plus 2 hydroxide. And now, since we have water on each side of our equation, we can cancel 1 water. And that in turn gives us the following balanced chemical equation. And we can check and verify this, and looking at this equation, are our atoms balanced in this equation? Are the atoms balanced in the following equation? Do we have the same number of atoms of each element on each side of our equation? Just as a brief check. Yes, perfect. Okay, so now that you have each of your half reactions in place, you're going to multiply each half reaction by an appropriate whole number so that the number of electrons in each half reaction are equal. So in this case, we have 3 electrons in one of our half reaction, 2 electrons in another. So we figure out the least common multiple. So what's the least common multiple of 3 and 2? What's the least common multiple of 3 and 2? 6. Yeah, 3 times 2 gives us 6. Note, when we multiply, the 2 applies to everything in our chemical reaction. Let's do another example. So looking at this next reaction, we have 2 and 5. What's the least common multiple between 2 and 5? Yep, so we multiply our top equation by 5, our bottom equation by 2. And let's show how this would work out. So we'd have 5 zinc solid plus 16H plus 2 MnO4 minus plus 10 electrons leads to 5 zinc 2 plus 2 manganese 2 plus 8 water plus 10 electrons. And as we notice quite clearly, the number of electrons on each side are identical and they cancel. If you've done everything correctly, your electrons will cancel. Does this make sense to everyone? Are the mechanics making a little bit more sense? Okay, so let's take a look at an example. Just for step 11, just as a formality, you add your 2 balanced half reactions together and you cancel out species that appear on both sides. Your electrons should cancel, and then finally just make sure that your reaction is balanced. Okay, so let's apply this to an example. So let's look at the following redox reaction, and we're going to balance this redox reaction. So first and foremost, we're going to assign oxidation numbers. So let's help me out here. Aluminum, what's the oxidation number of aluminum? 0. Hydrogen, what's the oxidation number of hydrogen in hydrochloric acid? Let's get a few more responses from the chat. Yep, +1. Okay, what about chlorine in hydrochloric acid? -1, yep. What about aluminum 3 plus? What's the oxidation number of aluminum? +3, yep. Finally, what's the oxidation number of pure elemental hydrogen? Wow, everyone's so fast. The moment I drew the arrow, the responses were already in the chat. Yep, for a pure element, the oxidation number is 0. Okay, what about chloride? What's the oxidation number of chloride? -1, right? For most cases, if you're just looking at a monoatomic ion, the oxidation number is equal to the charge. Okay, now let's try to identify the species that loses electrons. The oxidation number increases. So let's look at our oxidation half reaction. So what element loses electrons? What element loses electrons? Aluminum, right. So we have aluminum solid leading to aluminum 3 plus aqueous. Okay. How many electrons have we lost? How many electrons have we lost? 3. And since we lose electrons, what side of our equation do we place our electrons? The left or the right-hand side? The right-hand side, exactly. So we have 3 electrons on the right-hand side. Now let's try to identify what species gains electrons. What species is our oxidation number decreasing? We're looking at the reduction half reaction. So what species gains electrons? Hydrogen, yep. So we have H plus leading to H2. Now, before we go and count electrons, is this equation balanced in terms of atoms? Is this equation balanced in terms of atoms? No. So how many H plus atoms do we need? How many H plus atoms do we need? 2. Yep, perfect. So now, if we went from +1 to 0, how many electrons have we gained per atom? How many electrons have we gained per atom? So we have 1 electron per hydrogen atom. And how many hydrogen atoms do we have participating? 2. So 1 times 2 is 2 electrons. If we're gaining electrons, do we put this on the left or the right-hand side? Left or the right-hand side? The left-hand side. Okay, so now we have both of our half reactions, and now we have to figure out, what is our least common multiple? 6. So we multiply our top equation by 2, our bottom equation by 3, and we end up with the following modified equations. So we have 2 aluminum solid leads to 2 aluminum 3 plus aqueous plus 6 electrons. We have 6 electrons plus 6H plus aqueous leads to 3H2 gas. As we can see, our 6 electrons cancel on each side, and that in turn gives us 2 aluminum solid plus 6H plus aqueous leads to 2 aluminum 3 plus aqueous plus 3H2 gas. Perfect. And now we have our complete and balanced redox reaction. Notice how the redox reaction is a net ionic equation. So this chloride is just a spectator. So we don't have to worry about it in our net ionic equation. Is everyone feeling a little bit comfortable with this idea? Is everyone feeling a little more comfortable tackling redox reactions? Okay, so let's take a look and let's have you tackle the following redox equation. So this one's a little bit straightforward. We don't have to do any H plus and water adding for now, but I'd like you to try and balance the following redox reaction and really break everything down into the half reactions. I know you can balance this the normal way. This problem was intentionally designed so you can always crutch back on your normal method of balancing. But I'd like you to try and go through the steps to balance this equation from a redox perspective. And if you could just message me in the chat, how many electrons are gained and lost in our reduction and oxidation half reactions respectively. Just so I can see that you know how to count electrons when you're balancing these equations. And we'll spend about 2 to 3 minutes balancing this equation and really try to write out both of the half reactions. And you can always check your work balancing using the traditional method. This is one of the few redox equations where the traditional method will give you a correct answer. And don't be shy to message me in the chat your proposed balance equation, the number of electrons gained or lost. Whatever step you're stuck on, don't be shy to send me a message and I'll be happy to provide feedback during this open problem solving time. If not, we'll discuss in about another 30 to 40 seconds. Okay, so let's discuss this example. So first and foremost, before we do anything, we need to assign oxidation numbers. So in bromine, in elemental bromine, what is the oxidation number of bromine? 0, yeah. Okay. What about sodium? What's the oxidation number of sodium? +1. What is the oxidation number of iodide? What is the oxidation number of iodide? -1, exactly. Sodium, again, is +1. What about bromide? What's the oxidation number of bromide? Let's try to get some responses in the chat. Oh, -1, perfect. Sometimes there's a bit of a delay. And what is the oxidation number of iodine in elemental iodine? 0, yep. Okay, so let's look at our oxidation half reaction. So oxidation half reaction, we are losing electrons. So what species is undergoing oxidation? What species is losing electrons, is having its oxidation number become more positive? So bromine is being reduced because its oxidation number is becoming more negative, and iodine's being oxidized because its oxidation number is becoming more positive. So we have I minus leading to I2. So we're going from -1 to an oxidation number of 0. Now, before we do anything, is this equation balanced atom-wise? Are we balanced in terms of atoms? Do we have the same number of iodine atoms on each side? No, we need 2 iodines on the left. So then, my question to all of you is, how many electrons have we lost per atom? How many electrons have we lost per iodine atom? Oh yeah, yep. Two electrons would be the total numbers, but yes, we have 1 electron lost per iodine atom. We have 2 atoms, so that gives us 2 electrons. And do we place those 2 electrons on the left or the right-hand side? Do we place these electrons on the left or the right-hand side? If we're losing electrons, we place them on the right. Lose, I like to think of lose as produce. Okay, let's try now to look at a reduction. So in a reduction half reaction, we are gaining electrons. So what species did we say was gaining electrons? What atom did we say was gaining electrons? Bromine, exactly right. So we have bromine leading to bromide. So we went from 0 to -1. Now, before we do anything, is this equation atom balanced? Is this equation atom balanced? No. We need 2 bromide ions produced. So how many electrons have we gained per bromine atom? How many electrons have we gained for an individual bromine atom? 1, yep. And how many bromine atoms in total do we have? 2. 1 times 2 gives us 2 electrons. So what side do we put those 2 electrons on? The left or the right? If we're gaining electrons, it goes on the left. Okay, now all we have to do is rewrite our equations. And we add our equations together. Our number of electrons already cancel, so we get 2I minus aqueous plus Br2 liquid leads to 2 Br minus aqueous plus I2 solid. Perfect. So we have a completely balanced redox reaction. Any questions on this example? Any questions on this example? Okay, so let's keep going then. So let's try to do a more complicated example. We're asked to balance the following redox reaction, and we're asked to balance it in acidic or basic solution. So first things first, let's write our equation out and let's assign oxidation numbers. So let's start with the easy ones. What's the oxidation number of hydrogen typically? What's the oxidation number of hydrogen? +1. What's the oxidation number of oxygen? -2, yep. Okay, now to solve for the oxidation number of carbon, we're going to take our total charge, which is 0, minus the oxidation number of hydrogen times the number of hydrogens, minus the oxidation number of oxygen times the number of oxygens divided by the number of carbons. And that in turn gives us an oxidation number of carbon of +3. When you punched out this equation, does everyone see how I got +3 for the oxidation number of carbon? We're still using our oxidation number equation, except this time we're accounting for hydrogen and oxygen in our equation. If you want to make it slightly easier on yourself, you can break down this oxalic acid into H+ and oxalate ion and do the equation just for oxalate ion on its own. Whatever you're more comfortable with. Can I get some confirmation in the chat that everyone is comfortable with what I just did with regards to calculating the oxidation number of carbon? Okay, perfect. So let's now look at permanganate. The oxidation number of oxygen is going to be what? -2, okay. And would everyone mind taking just like a minute to calculate the oxidation number of manganese using our oxidation number equation? And don't be shy to propose the oxidation number in the chat. Oh, perfect. Everyone's pretty fast at this. So manganese was a proposed oxidation number of +7. So just to show the logic behind this, the oxidation number is equal to our total charge, which is -1, minus the oxidation number of oxygen times the number of oxygen atoms over 1, which gives us an oxidation number of +7. Perfect, perfect. Now let's do some freebies. What's the oxidation number of manganese? +2. Okay, what's the oxidation number of oxygen? -2. And in order for our oxidation numbers to equal the total charge of our molecule, would someone like to propose the oxidation number of carbon in carbon dioxide? +4. Yep, perfect. Okay, now let's look for what species loses electrons. So losing electrons. So this is the oxidation half-reaction. So what species is losing electrons? What species is losing electrons? What atom is losing electrons? What atom is increasing in oxidation number? Carbon, right? So let's put every species, every molecule that has carbon. Now, before we get started with any complicated electron balancing, is this balanced in terms of atoms? Do we have the same number of carbon atoms on each side? Don't worry about hydrogen and oxygen for now. Just focus on carbon. Do we have the same number of carbon atoms on each side? No. We have, how many carbon dioxide molecules do we need for a balanced equation? We have 2 carbons on the left, so we need how many on the right? 2. Yep. Okay, so let's now look. We went from +3 to +4. So how many electrons have we lost per carbon atom? How many electrons have we lost per carbon atom? One. And we have how many carbon atoms participating in this process? How many carbon atoms are participating? We have 2 carbon atoms on each side. 1 times 2 gives us 2 electrons. If we lose 2 electrons, what side do we place our electrons? The left or the right? The right. Okay, perfect. However, rewriting this equation, we still have a little bit of work to do. Are all of our atoms balanced? Are all of our atoms balanced in this case? Do we have the same number of atoms of every element on each side? No, we need to balance hydrogen. And in order to balance hydrogen, we add H+. So how many H pluses do we need to add? If we have 2 hydrogens on the left, how many H pluses do we need on the right? How many H pluses do we need to add on the right? 2. Okay, perfect. And here we have a balanced half reaction. Let's do the same thing for permanganate. So we're going from MnO4- to manganese 2+. So in this case, we are losing electron. Oh, whoops, no. So in this case, manganese, we went from +7 to +2. So we are gaining electrons. So this is a reduction half reaction. Okay, so how many electrons did we gain in this process? How many electrons did we gain in this process? if we went from +7 to +2? Five, exactly right. Okay, now we're going to rewrite this equation. Now we're going to rewrite this equation. And now my question to all of you is, to balance oxygen, if we need to balance oxygen, what do we add under acidic conditions? What do we add under acidic conditions? What do we use to balance oxygen under acidic conditions? So hydroxide is used under basic conditions, but what do we use under acidic conditions? To balance oxygen. So we use H+ for hydrogen, and what do we use to balance oxygen? What is our oxygen source under acidic conditions? Make sure to flip through your notes, and water, exactly right. So if we have 4 oxygens on the left, how many waters do we need to add? How many water molecules do we need to add? How many water molecules? 4. Okay. And now that we've balanced oxygen, let's now balance hydrogen. So we're going to balance hydrogen with H+. So then, what do we need to add? How many hydrogens do we need to add? How many H+ do we need to add? So we have 8 hydrogens on the right. So how many hydrogens do we need to add to the left? 8. Okay, perfect. So let's just take each of our equations now. Let's take each of our equations and let's write them in close proximity to each other. So we have both of our half reactions that have been balanced with respect to atoms. Now what we have to do is we have to find a least common multiple between our number of electrons. So we have 5 electrons in our reduction reaction. We have 2 electrons in our oxidation reaction. So what is our least common multiple going to be? What is our least common multiple going to be? 10. Yep. So we multiply the top equation by 2 and the bottom equation by 5. And that in turn gives us 16H plus 2 MnO4 minus plus 5 oxalic acid molecules plus 10 electrons leads to 2 manganese 2 plus 8 H2O plus 10 CO2 plus 10 electrons plus 10 H plus. And now, do we have identical species on each side of the equation? Do we have identical species on each side of the equation? Can we cancel our electrons? Yeah. So what else can we cancel? What else can we cancel? Is there anything else that's exactly identical on each side of this equation? Is there anything else that's exactly identical on each side of this equation? Anything else that's exactly identical? So if we compare the left and right hand side, is there anything else that is the exact same chemical species on each side? Well, I see H plus right here. So I'm going to cancel 10H plus from each side to leave 6 on the left. And with that, we have a complete and balanced redox equation that we'll write one more time after we've finished modifying it. So we'll look at how to balance these equations under basic conditions in the next set of examples. And if you want, you can always just go through your equation and check that it is in fact balanced. Okay, any questions on this example before I let you loose to work on an example of your own? Okay, so let's let you loose on the following problem. So I'd like you to take a look at the following reaction, and I'd like you to start and give your best attempt at balancing under basic conditions. So in this case, you use OH minus and water. Don't worry, worst case, you can always start balancing the equation under acidic conditions, and I'll show you how to convert it into a basic set of half reactions. So let's spend about 4 to 5 minutes working through this problem, and you're more than welcome to message me your proposed half reactions. If you even want to try drawing out and writing on this shared screen, you're more than welcome to use the annotate feature available on Canvas. Available as part of this Zoom streaming. But I'd like to see some communication either on the number of electrons gained or lost, what you think the oxidizing agent is, what you think the reducing agent is, or you're even welcome to type out your proposed half reactions. So let's spend about 4 to 5 minutes working on this problem, and then we'll come together as a group to discuss. And don't be shy to message any questions. We'll discuss in about 3.5 minutes. Any questions so far in identifying the oxidizing and reducing agent? We'll discuss in about a minute and a half, but don't be shy to send me your proposed balanced equations. I just want to give everyone a moment to try and write down a reasonable response, so that way when we discuss, we can compare our problem-solving methods, and I can answer any questions you may have. Okay, so let's discuss this problem. So first things first, I'm going to rewrite my equation. This is one of those fun reactions that looks like it's balanced or looks very close to being balanced, but requires you to think very carefully about the electrons gained and lost in each step. So let's go through and assign oxidation numbers. So what's the oxidation number of cadmium? Pure cadmium. 0, yep. What's the oxidation number of nickel in nickel 3 oxide? +3, yep. Oxygen is -2. What's the oxidation number of cadmium in cadmium hydroxide? What's the oxidation number of cadmium in cadmium hydroxide? +2. Okay, and what's the oxidation number of nickel in nickel hydroxide? Two, yep. Okay, so let's now look and let's just focus on the species that lost electrons. So lost electrons, so we're looking at the oxidation half-reaction. And my question to all of you is, what species lost electrons in this process? What species lost electrons in this process? What species is increasing in oxidation number? Cadmium, yep. So we have cadmium solid leading to cadmium hydroxide. And how many electrons did we lost? How many electrons did we lose, or how many electrons were lost when we went from 0 to +2? How many electrons did we lose? 2. And where do we put those electrons? On the left or the right-hand side? Right, yep. Okay, now we need to balance oxygen and hydrogen, and we're going to balance oxygen under basic conditions. So what do we add if we want to balance oxygen under basic conditions? What do we need to add to balance oxygen? Water, that's one option. We can use water, or we could use hydroxide. And if I had to take a guess, hydroxide seems a little bit easier to balance. So then, if we have 2 oxygens on the left and, 2 oxygens and 2 hydrogens on the right, how many hydroxides do I need to add to the left? How many hydroxides do I need to add? 2. Perfect. So this equation is all balanced and wrapped up nicely. So let's look next at the species that gained electrons, and let's look at our reduction half-reaction. So what species gained electrons? What atom gained electrons? nickel. So we go from nickel 3 oxide to nickel hydroxide. Okay. Now, before we do anything, is this equation balanced? Is this equation balanced? So we went from, do we have the same number of nickel atoms on each side? No, no, clearly not. Okay, perfect. Now, if we go from +3 to +2, how many electrons have we gained per nickel atom? How many electrons have we gained per nickel atom? 1. And we have 2 nickel atoms leading to 2 electrons gained. What side of the equation do we place those 2 electrons? The left or the right? The left. Yep. Okay. So now I'm going to rewrite this equation since we have one more thing that we have to take care of here. So we have to balance this equation under basic conditions. So as bookkeeping, we have 3 oxygens on the left, and we have 4 oxygens and 4 hydrogens on the right. Okay, so we have some motifs to work with. Remember, if you want to add 1 oxygen to the right, or let's suppose if we want to add 1 oxygen to the left, you use the following pair. If we want to add 1 hydrogen to the right, we use this pair. So then, if we need to add let's add a few more pieces of information. If we need to add 1 hydrogen to the left, we'd use this pair. So then, my question to all of you is, how many oxygens do we need on the left? How many oxygens do we need to add to the left? How many oxygens? We do need 4 hydrogens on the left, and we'll get to that in a moment, but how many oxygens do we need on the left? 1, okay. So what I'm going to do is I'm going to add 2 OH and 1 water. Okay, so I've checked off my oxygen. If I need to add 4 hydrogens to the left, what I'm going to do is I'm going to add 4 waters and 4 hydroxides. And that in turn gives us the following equation. So we have 2OH plus 4H2O plus nickel 3 oxide leads to 2 nickel hydroxide plus H2O plus 4 hydroxide. Then we cancel our hydroxides and we cancel our waters. So in turn, at the end of this process, we have 3 H2O plus nickel 3 oxide leads to 2 nickel hydroxide plus 2 hydroxide plus 2 electrons. Okay, now what we're going to do is we're going to rewrite our previously generated equation for cadmium. Oops, one moment. So we're going to rewrite this equation for cadmium. So we have cadmium plus 2OH minus leads to cadmium hydroxide plus 2 electrons. Our number of electrons cancel. So all we have to do is add this equation together. Hydroxide cancels because we have the same number of hydroxides on each side. And we get our final equation after balancing to be 3 water plus nickel 3 oxide plus cadmium solid leads to 2 nickel hydroxide plus cadmium hydroxide. And as we can clearly see, the number of atoms of each element is balanced. So this is our complete balanced redox reaction. This is why I gave you these nice little tool tips for balancing hydrogen and oxygen under basic conditions, as students often have a lot of trouble with basic balancing. Does this example make sense? Does the logic behind it make sense to everyone? Does everyone understand why we chose to add each of these motifs to each side of our equation to balance the number of oxygen and hydrogen atoms under basic conditions? So we went a little bit over today, but this is the end of our lecture period. We're going to take a 10-minute break. So I'll see everyone at 2:35, and then we'll come together in lab for another lecture slot. So we'll spend about maybe an hour and a half of additional supplemental lecture in laboratory. So I'll let everyone take a 10-minute break, and I'll see everyone at 2:35 in laboratory.